Last time we were looking at the electron, but this time we're going to focus on the nucleus of the atom. So this is the model of the atom that probably kind of springs to mind. We call this the Bohr-Rutherford or Rutherford-Bohr model. Now, prior to this, there were loads of different models that have been developed to try and conceptualize what the atom looks like. And even the one we work with today is just that. It's just a model, a way of thinking about something that is really hard to get your head around. So previous to the model of the atom that we're familiar with today, we used to think that the atom was more like a plum pudding with a giant sphere of positive charge dotted around with electrons all the way through it. Now we currently more go with the Rutherford-Bohr model. So the evidence for this is mainly down to Rutherford's experiment originally. So what he did was he took a kind of thin sheet of gold foil. And he chose gold because he can draw it out in a very thin sheet. And he bombarded it with alpha particles. Now we're going to talk more about alpha particles later on, but for now they're just positively charged particles. And when they hit a fluorescent screen, they kind of fluoresce, cause a scintillation, little spark of light. So what he did was bombard them and kind of saw what happened based on where the sparks appeared. When Rutherford did this experiment, he found that the vast majority of the alpha particles that he shot at the gold foil, the vast majority of them just went straight through, completely unaffected, just straight through, no deflection of any sort whatsoever. He did find, though, that some would change their course slightly. And they're being deflected by something. Now, the beauty is we now know what they are, but he retroactively figured this out. Very, very rarely, one of these alpha particles would also get deflected, not just a little bit, but a lot, to a greater angle. Now, we know now that's because you got the positive nuclei repelling the positive alpha particle. And a quick note here, nothing here is to scale. Everything's been exaggerated to the fact that we can see it. Relative to each other, they'd be very much further apart and very much smaller. Here's a neater diagram of Rutherford's results and what he found out. Now, one of the things he was able to determine from his experiment by looking at the amount of particles that were deflected and the amount they were deflected by, he was able to make an estimate of the radius of both the nucleus and the atom as a whole. And if you look at the numbers, the radius of the atom is approximately about 10 to the minus 10 meters in terms of order of magnitude, and the nucleus about 10 to the minus 15. That's a big difference. It's 5 orders of magnitudes in the difference, so 100,000. So the atom would be 100,000 times wider than the nucleus. That's why we kind of think of examples to try and help conceptualize this. So we'd say if the nucleus was the size of a marble, the whole atom would be the size of, let's say, Croke Park or another stadium, with the electrons being in the outer ring. And this model, the Rutherford-Bohr model, has been overwhelmingly supported by experimental evidence, so it's what we kind of roll with today. You guys are probably already quite familiar with this model of the atom that we've been using. You've got the protons and neutrons in the densely packed nucleus and the electrons in a kind of ring, shells going around the outside. And you've probably already also looked at being able to kind of create tables like this, where you look at the particle's location, relative charge, and relative mass. Probably at junior cert you've looked at stuff like this. Now we're just going to kind of elaborate on it a little bit. So instead of looking at relative charge, we know that an electron has a charge of 1.6 by 10 to the minus 16 coulombs of charge. So we know the absolute charge on an electron, and therefore because the proton has the opposite charge, we know its amount of charge too. We can also quantify the actual mass of a proton and a neutron. And we're going to come back to this later on in another part of the lesson, but for now, just that we can be a little bit more exact than the relative masses and charges that we were talking about earlier on, even though they still have their uses massively. No pun intended. A quick note here on something to pay attention to, that the mass of the neutron is ever so slightly more than that of the proton, and we're going to come back to this later on, but just to note there's a little bit of a size difference there. Before we go any further, we have to refamiliarize ourselves with the periodic table of elements developed by Mendeleev. You've probably seen this before, in fact, you've definitely seen this before. You looked at this as junior cert, we just need to be really familiar and comfortable with it now. So on the periodic table is basically all the stuff that has mass, anything. So everything that makes up you, me, the stuff around you, the air that you're breathing in, is all made up of things that are found on this periodic table. So the elements are organized into groups, which are the columns going up and down, and also into periods, which are the horizontal rows going across. What determines which groups and periods they're placed into is down to firstly their atomic number. So on a very simple periodic table like this one, it'll usually just have one number on it, and that refers to each element's atomic number, which tells you how many protons that element has in its nucleus. Now, as you're going to find out in a little while, electrons can come and go, even neutrons can alter, can vary, but what determines which element you're dealing with is how many protons it has in its nucleus. That's what, by definition, that's what makes it an atom of that particular element. So if you look at, as you go across on the periodic table, the atomic number should go up by 1 each time. And then when you reach the end of each period, you have to go to the next period down. And again, the number will keep increasing by 1. So as you go along the periodic table, its atomic number will increase. Each element's atomic number will increase by 1 each time. More advanced periodic table that you can see in leaving cert texts will also include a mass number, a second number on there. And it's the convention is usually that we have the mass number above the symbol, unlike in this example here. But it doesn't really matter because it's always going to be the larger of the two numbers. So what exactly is the mass number? The mass number tells you how many protons and neutrons there is in the nucleus of that in the nucleus of an atom of that element. Now, already you might notice something a little strange there. See that the decimal place. So you can't really have part of a proton. So there's something strange going on there. So let's have another look. Let's take a look at these two atoms first. We've already ignored the electrons. We're just looking at their nuclei. And also let's just ignore the neutrons for a minute and have a look at the protons. And you should notice something strange. They both have the same number of protons. They both have 6. But they do have a different number of neutrons. The first one has 6 neutrons. The second one has 8. So going back to the protons, they both have 6 protons, which means their atomic number is both 6, so therefore they're both carbon atoms. But they do have different amount of neutrons. Now this can happen, and they refer to as isotopes. Iso for the same. So they're the same number of protons, but differing number of neutrons. To differentiate between them, we sometimes just refer to them by their mass number. So you might hear like carbon 12 or carbon 14. So let's revisit why there's a decimal place in the mass number of elements of the periodic table. The reasons there is the periodic table shows the weighted average of all the isotopes for that particular element. So for example, between carbon 12 and carbon 14, there's a lot more carbon 12 around than there is carbon 14. So the weighted average would therefore be much closer to 12 than it is to 14. One of the reasons for this disparity in abundance of each isotope, why you get so many of one particular isotope and not of another, is because some are just more stable than others. So if something's more stable, it'll generally have less energy. And the isotopes that are more stable will have less energy than the isotopes that are unstable. So if an atom of an unstable isotope can get rid of this energy somehow, it can become more stable. And in the process of doing this, it can actually change from being one element to another by changing the amount of protons in its nucleus, which we're going to look at now. So how they lose this energy is by emitting nuclear radiation, which we're going to look at in a little bit more detail in a moment, but it comes in 3 flavors: alpha, beta, and gamma radiation. When an atom emits nuclear radiation, it's said to undergo radioactive decay. That's regardless if you're talking about alpha, beta, or gamma radiation. So let's look at alpha first. So alpha radiation is when an unstable isotope emits an alpha particle. Now an alpha particle is 2 protons and 2 neutrons kind of bundled together. If you think back to Rutherford's experiment, that's what an alpha particle was. So 2 protons and 2 neutrons are ejected from the nucleus of the atom. The alpha particle will move away at high speed, and it's worth noting here that the alpha particle with 2 protons and 2 neutrons is essentially a helium nucleus. Okay, let's have a look at what happens when an atom emits beta radiation. So if you remember back, we said that the neutron is very slightly bigger than the proton. So in beta emission, what happens is a neutron can actually break apart really into 2, into a proton and an electron. The electron is ejected at high speed from the nucleus, and the proton remains in the nucleus. So a neutron is essentially turned into a proton. Finally, when an atom emits gamma radiation, its nucleus doesn't change. It just emits a brief burst of high energy electromagnetic radiation, very high frequency, even above that of an X-ray. In terms of their behavior, if they encounter an electric field, well, the alpha particle is positively charged because it's got 2 protons, and the beta radiation is an electron, so it's negatively charged, and the gamma radiation doesn't have a positive or negative charge. So they behave as you'd expect a positive or negative charge particle to do. So in that electric field, the positive will be attracted towards the negative, and the negative will be attracted towards the positive. So they'll deflect. whereas the gamma radiation won't because it doesn't have a charge. Similarly, if the radiation encounters a magnetic field, they'll also behave as a charged particle would. So they'll deflect according to Fleming's left-hand rule, and again, the gamma radiation, not being a charged particle moving in a magnetic field, won't experience a force, whereas the other two will. We'll be looking in a lot more detail at ionization in the second part of this lesson, but for now, ionizing power of the radiation is just how much they can make the particles they encounter become ions. And you'll find that the alpha is very ionizing, the beta is medium level of ionizing, and the gamma radiation isn't very ionizing at all. So it's how much they can make the things they encounter into ions. And again, we'll be coming back to that in a lot more detail later on. In terms of how far each type of radiation can penetrate into different types of matter, again, they behave as you'd expect given their relative masses. The alpha particle has a lot of mass comparatively with the 2 protons and 2 neutrons, so it can't penetrate that much into materials. The electron can penetrate a little bit in because it's quite small, it's an electron, and the gamma radiation can penetrate through a lot of material. It usually takes a couple of meters of concrete or a big block of lead to stop it. Whereas the alpha can be stopped even just by a few centimeters of air or a thin layer of paper. And to stop the electron, you just need a bit of aluminium foil, or again, it doesn't take much, whereas with the gamma, it takes a lot. It might be worth just pausing here for a second and making sure that all the features of this table are familiar to you and you're comfortable with them. Finally today, we're going to look at how emitting the beta and alpha radiation can change the composition of the atom. So emitting gamma doesn't really change how many neutrons and protons you have, it just changes their arrangement. But if you emit alpha or beta radiation from an isotope, there's a change as to how many protons and neutrons there are in the nucleus. So let's start with beta emission. So if you think back to that carbon-14, an atom of the carbon-14 that we talked about earlier on, it'll undergo beta emission. So it'll emit an electron after a neutron has turned into a proton and electron. So that's increased the stability of the atom. But can you really still call it carbon at that point? Because if you add up how many protons it has now, it's got 7 protons. It's not carbon anymore. It's now nitrogen, N14. So let's look at a more generalized example of how that happens. So in these nuclear equations, where you try and see what happens to each atom, the convention is that the mass number goes above the element and the atomic number goes below. Now, confusing enough, the A here stands for the mass number, even though you think it should be atomic, and the Z stands for the atomic number. So we refer to the nucleus that's about to undergo radioactive decay as the parent nucleus. And the product that it produces is called the daughter nucleus, and we'll call that element Y. So for beta emission, the parent nucleus has had its mass not be affected, but it has increased its atomic number by 1. And don't forget that there's an electron emitted as well. Finally, let's look at how emitting an alpha particle via radioactive decay affects the atom of a particular isotope. So again, we have the parent and the daughter nucleus, X and Y, and it's going to emit an alpha particle that is a helium nucleus with 2 protons and 2 neutrons. So that means for the parent nucleus, its mass is going to go down by 4 because there's 2 protons and 2 neutrons lost, and its atomic number is going to go down by 2 because it's lost 2 of those protons. Don't forget when you're doing these to write in the alpha particle too, the He42. I know this has been quite a heavy batch of stuff to get your head around. To finish with for today, I'd like to have a try at the questions on 351 and 352 of your textbook. I think it's 30.1. I'm going to go through them as well and then put these solutions up on Edmodo like last time. For now, just take care of yourselves, and if you have any questions or problems, don't hesitate to contact me. Talk to you soon. Bye.